variance matrix. And for example, the Bernoulli distribution, we just want to know the likelihood of throwing a tail or a head. And we just need to know one parameter to estimate this. Okay? All right, and we talked about the fact that in many cases we just take the log of this function here because, first of all, it makes it easier. It makes our independent distributions into a sum, but also in the case of the Gaussian distribution, it gets rid of the exponent, which is kind of ugly and sometimes numerically difficult to handle. We had an example where basically have a coin toss example where the probability of x is given by p to the power of x times 1 minus p 1 minus x, and that's basically the way to formulate this, while x is in 0 and 1. So these are basically do you throw an event 1 or do you throw an event 0 is dependent on only this parameter p. No other parameters are required. For the expected value of this, well, obviously, or logically, the expected value has to be p in this case, and the variance is p times 1 minus p. And so, but we do not have access to this variable here most of the time, so we have to estimate it. And we can estimate it, well, you might have guessed, by just basically taking our sample, looking at all the times that we threw a 1 or a 0, and then depending on if we want to calculate the p for the zeros or the ones, we take basically the sum and divide it by the number of throws. Very simple. For this coin B, for example, we have 2 sets of observations. Each of them have 10 throws. In one case we have 5 heads, 5 tails, 4 heads, 6 tails. In the other case, that gives us a 9 heads and 11 tails distribution, and basically that gives us a p value of 0.45. But clearly, a couple of things that you see immediately are, for example, and this is in the case where p is the likelihood of having thrown a head. If you do the tails, obviously you get 1 minus this, right? But if we stopped here and we only had these 10 throws, the p-value would be very different, right? It would be 0.5. And if we only had this one, it would be 0.4. So obviously, what we can see right away is that the larger our sample is, the better our estimation of the likelihood that we pick the right target p, or the best estimation is dependent on the size of your sample. So that's kind of one of the arguments why more data is better data, or there is no data like more data. For the coin A, we have even more observations, and this coin seems to be a modified coin that is not a fair coin, while B could very well be a fair coin, just with one outlier here. Okay, so this is kind of how you do maximum likelihood estimation on Bernoulli, and basically what you can do with that then is I can ask you questions like, okay, so what's the likelihood that you're going to observe in the next coin toss, like a head or a tail? And for B you would say 0.45, and for A you would say 0.8, right? So this is kind of what you can use this for. In Gaussian distributions, we can and obviously this is not classification, right? But we're gonna get to that, and we got to that in the last lecture as well, how we can use these estimated distributions and parameters for classification or for prediction of like which class a certain item belongs to. That's kind of like the parametric classification problem, but this is just like maximum likelihood estimation. Okay, so for Gaussian densities, well, Gaussian curves are dependent on, so they're normal distributed, that's why the n is here, and then they're dependent on two variables, in this case mu and sigma, and sigma square basically is the variance. In this case, sigma is just the standard deviation of the sample, and then the probability of a value x basically can be computed with this function here. So this function obviously is this Gaussian curve or around a certain point, and so it's symmetric around the middle point, which is mu. So that's the mean value, and has some sort of like certain width, and it can be flatter, it can be sharper depending on the sigma parameter. Okay, that should be fairly clear to everybody. So now the log likelihood can be expressed by just adding the log to this whole thing, and basically what we end up with is this nicer function which basically has a more or less constant term. It's just dependent on the number n, which is our number of observations, I guess, and like the variance here or the standard deviation here, and it doesn't have this exponent anymore. If you want to estimate the mu and the sigma values, you basically just compute what you have learned previously. You just compute the mean value and the standard deviation of the observed sample to basically get towards the actual underlying sample that we do not have access to. Just an important note that usually we use Greek letters for the actual underlying distributions of mu and sigma. That's the actual values, and then m and sigma, s for the Roman letters for the estimated ones. Okay, so how can we use this for classification? Well, one of the things that we have learned previously is basically that we want to compute the posterior of a given observation to belong to a class Ci. And to compute this, we basically can apply Bayes' rule to kind of turn this around. Now we have likelihood here, which we just talked about, the prior of the class here, and basically the evidence for the observation x here. And you can already guess it. So okay, if I want to compute this, well, I don't really need this here because it's going to be the same for all the classes, so it's independent of the class. So I can already kind of strike this away and basically come up with a discriminant, gi of x, that's the likelihood times the prior, and we can also apply the log to make this multiplication into a nice sum, so that's beautiful for us. And then if we replace this posterior with this likelihood with a Gaussian, we receive this term down here. And if you want to use this as a discriminant, well, the cool thing already is like this constant term here falls away. This one is remaining. However, we can sometimes make assumptions that we believe that all the data points are from the same distribution or have the same variance, so we could remove these parts. If we then even assume that all the data points have similar priors, we can even remove this guy here, and then we only have to estimate it based off of the mu value. Yeah, so that previous function had the sigmas and the mu's, but we need to estimate these. And the only difference why there's now an r here is because basically the observations belong, they don't just have x values, but they also have a label value. And so we need to compute the mean values and the standard deviations or the variances based off of only the values that belong to that class I. So every class is a different mean value now. And that's why we have this indicator variable, and like the indicator is 1 or 0 for like it's a multi-dimensional, like a k number of observations, number of classes, dimensional vector that's 1 for only one, 0 for all the others. So you can sum this up easily. And then standard deviation or variance can be computed the same way. The prior is just the number of observations that belong to class I divided by the total number of observations.
So we're reducing this to a distance problem.
Exactly.
We just calculate the means of all the labels.
Yeah.
And we are figuring out the distance.
Yes. And so that's exactly what you're doing. However, you're evaluating, or like you're weighing it, or you give it weight based on the variance, right? So if a class is a very large variance, the distance to the class mean value doesn't have that much weight, right?
You're accommodating for the density of data.
Exactly. Yeah.
That's interesting.
Yeah. And basically, this is exactly what this now says here. So the constant here, this value falls away, so that's the same for all the ones. If we assume equal priors, we can remove this. And if we assume equal standard deviations, well, we can remove these parts here as well. And then we end up with just this value here. And we basically can just choose for all the classes which one has the minimal distance to its mean value. So, and then if you have two classes, you can even reduce it to this kind of structure here. And that's kind of like the midpoint where you are uncertain between, and it's the midpoint between the two mean values. And so yeah, like that basically just tells you how far are you away on either side of the mean value with your observation that you want to classify. Does it go into this one or does it go into that one? And you can see this visualized here, where the only difference between those two classes, 1 and 2, are the following. It's like the mean value is either -2 or +2, but they have the same variance, they have the same prior as well. So if this one would be wider, right, like you would have like something like this, then that would obviously make a difference. Like you would have to use like the, you would have to basically imagine that this line is like more like this, okay? So less steep in this case. And so the distance from this point, if the distribution was much wider, if it was around here, like you could still have some support for this other class, even though it does look like it's further into the other territory. So the likelihood is there. And the interesting part about these classifiers also that even if we're like around here, well, we have a likelihood of it being class 1 with like 0.7, but it could also be the other class with 0.3, right? So it's not that you're giving like a direct crisp classification. So a crisp classification would be if you cut off those, if you do the following here, right? If you do this, you're crisply classifying that. You say it's either one or the other. There's no support for any other class there. But if you don't like make this Boolean assumption basically, where you say I want to take the minimum, if you just say like I want to allow both of them to go through and like I have like 0.7 support for this one, 0.3 support for that one. You can actually use that, and that's one of the things that we might be also talking about a little bit. Basically, like one of the things that I worked on a few years ago, maybe going back to that because it's kind of interesting, is fuzzy machine learning. So fuzzy machine learning is where you do not assume these things anymore. Like you don't say it's one or the other. You always say, okay, it could be any of them. It could be a set of observations. And that's particularly important if you do not really know what the ground truth is and you only have an opinion about it. And so like the work that I did with this was, for example, emotion classification. We had samples of like people talking, and we had like a set of 5 experts, PhD students, myself, M-Turkers, online and stuff like that, look at these videos or samples, and then we had to say, okay, oh, I think this is depressed, or this is happy, this is angry. And then like everybody has a different opinion, but people kind of correlate with each other. And so like what a lot of other researchers do is they just take the majority vote. And they say, no, it doesn't matter, like I don't care what everybody else said, I just want to take the majority vote. But that's often wrong, because I think there is, or like the theory that we have is like, we believe that there is some value in the confusion. So if you have a observation where everybody says, no, that's happy, like there's no confusion, there's no, like, everybody has the same opinion about it, so that's a clear case. But if like people are like 50-50 or like 75-25 or 70-30, there might be like, they might indicate that actually this point is closer to neutral or to angry or like sad than the other point was. So these labels might actually have meaning, so that kind of goes into that direction. Then we have like made some like we like built a fuzzy support vector machine back in 2007 or 8. Yeah, that one's kind of that was useful in that case, but support vector machines are dead, unfortunately.
They are?
Kind of. Try big data on support vector machines.
Yeah, that's
I
gonna
think
be,
you're
yeah,
gonna be
yeah.
happy. Okay, but I like support vector machines. Like
Prefers
they are,
stuff.
because they always have an analytic solution, right? Like you can, you don't have to validate much with them, and you don't have to run them 100 times. Okay, but yeah, there is no. I think there might not be any support vector machine.
But what about the boosters? There's so many applications where you don't really need machine learning to go through a zillion sets, but you need kind of a human logic built into a system. And then you have smaller sample, and smaller sample will teach the program to have the discriminant closer to human, or you can do boosters. So then,
I think if you start thinking about these new or like different ways of giving them a better idea and stuff like that, I think it gets more useful. And actually, to use human knowledge, we're gonna come to graphical models hopefully later today, where human input is very important into like designing them. But yeah, we can have these special topics. Okay, so like we also talked briefly about regression. In this case, in regression, we are not approximating. We're not approximating a distribution function, but we're approximating basically a function that is kind of noisy with some additional noise information that we do not have access to. We can't really model that. And so what we want to learn is basically a function g. It has again some parameters, theta, like that could be variably many parameters, and we want to approximate this function f. One of the things that we assume, though, is that that there is some like random noise that is sampled around these values x. So we believe that the actual value, and this comes from this one here, the actual value that we want to approximate is kind of like around or somewhere within a boundary around the observed value x. And this can be modeled through this kind of function here. To illustrate this, basically, it's the following. So we have these observations here, but we are not sure where the actual value is. So the actual value might be somewhere in between, and we would assume maybe if this is the right model to estimate this function f, then, well, this would be the right value for it. However, the thing, or the reason why we do this is because if we attempted to find a regression model where we always believe that the observed values are always taken at face value, like we always need to hit them, because otherwise we're not like modeling it correctly, well, we would never be able to find a linear regression through those models unless they are really nicely aligned on a line. So it doesn't really make any sense to believe that the values that we observed are the actual true values, okay? Because like otherwise it doesn't, like we would have to find functions that go through these things. So we could never fit a simple function unless they are really simple problems. Okay, we basically can estimate this again in a similar fashion, and we can again compute the log likelihood of these like noises, and what I would like to like basically mention, no problem. Basically mention that if we have linear or ordinal problems for like polynomial problems with a certain level of orders, we can always compute these values or estimate those values using linear equation systems, which can basically always be either written in this form or written in vector matrix notation, and we can always find an optimal solution for these problems. Okay, that's just like basically just housekeeping. So like if you want to estimate the function through like a linear function where we have two parameters, so we have a bias and a weight, or we only need two, and then we can calculate it through these two variables there. But if we could also do like a quadratic, so we would have a third parameter here, and so on. So we would just, instead of like having just two weights, we have three weights, and then we have the sum of r, sum of rx, sum of rx squared, and in this case we would just add like a new column and a new row. Okay. All right. So then we also briefly discussed multivariate methods. I don't want to go into too much detail here again. Basically, we assume that our observation sample, or a sample that we observe, is not just now like a series of single observations, but a series of vectors. So we can actually write our data set as a matrix with d dimensions, and n samples. So usually we have dimensions in the columns and the observations in the rows. Then we can estimate not just one like mean value, or like there's underlying, so because these are the Greek letters, so this is the true values. As not only underlying one mean value, but actually a series of mean values, and we don't just have a single variance, but we have a matrix of a covariance matrix that has the variances on the diagonal and the covariances on the like off diagonal, and this matrix is also symmetrically across the diagonal. So this like D1 and 1D are the same values. Okay. And so oftentimes, yeah, so basically this just gives you an idea of like if the variables are correlated linearly or not, depending on -1 + 1, etc. And so from the univariate case, we basically just extrapolate this problem out to the multivariate case, and it's simple again to compute these mean values and variances and covariances based off of the sample and the sample correlations. This just yeah, and so now our density function becomes a bit more complex with the covariance matrix here. So it's kind of like normalized again by the variances of the certain like combinations of independent variables, and then we have the distance to the of the observation to the new value again to calculate the distance between the observed data point x and the multivariate mean values. And this also basically reflects the Mahalanobis distance, which basically weighs the distances based off of the variances. So large variances like measure this distance less. Okay. And oftentimes it is, like most of the time, it's kind of like too difficult to compute the full covariance matrix, and like we might sometimes don't even have enough data to do so. And so like I have this slide here where basically we discuss like what happens if we, for example, set the covariances, which are these two guys here, if we set them to 0, and basically that means, and if we set the variances equal, then we basically like have circles in our observations. So like when you compute the distance for a data point like here, you evaluate all of the dimensions the same way, so it's kind of like circular. If we have one variance being larger than the other, but we stretch the circle in a certain direction, either we create this shape or we create this shape. And then if we have a covariance that's greater than 0, or we turn it into an orientation where the two variables are positively dependent on each other, so if one goes up, the other goes up. And if we have a covariance that's smaller than 0, we basically have a negative relationship, so if one variable goes up, the other one goes down. Okay? So that's kind of what these different covariances, covariance matrices can represent. And you might have guessed it already, so if you have a certain data set and you want to basically like approximate your observations, you want to compute the covariance based off of a sample, and you have a limited number of data points, but you have a high number of variables. Well, often it does not make sense to compute the full covariance matrix. Sometimes you just want to compute the diagonal matrix, which basically just measures the variances of each variable separately. Or you even assume that all the variances are the same. So you simplify your model over and over if you remove those variables, and that basically means that you are kind of preventing overfitting, but you might get into the territory of underfitting. Okay, so that's like this trade-off again. Do I want to model the entire covariance matrix or just a part of it, and so on. And I'm going to come to this for hidden Markov models. where oftentimes you have to make these decisions, and I think most of the time we're going to just compute the diagonal. It reduces computation time, it's like less likely to overfit and so on, okay? All right. Yes? Other questions for that?
How can we use like the covariance to compute like to help the classification?
Well, it's the same way actually. It's the same here, where basically you have so you want to again compute the posterior, and then you use this likelihood, you estimate the covariance, you estimate the mean values, and then and actually we're going to come to this in the next slide. So yeah, so basically you use the same approach as for the univariate like discriminant function, which is this one here, right? But then instead of this one being univariate, this now is a multivariate problem. So this is the actual one, and then we need to estimate the m's and the sigmas and the priors for all the classes. And instead of like this being one value and this being one value, this is a matrix and this is a matrix. And in this case, I think we probably decided that this is going to be, and also there should be another I. Yeah. And then, yeah, so this should be like the SII, I think. Yeah. Yeah, so, oh, yeah, this is actually a capital S, sorry. Yeah. Yeah, this is a capital S, sorry. And the I doesn't stand for the variables anymore, so, but for the classes. I should have made that clear. So this is a bit, I need to work on the indices. So these I's here now are for the classes, so each class is a vector of mean values and a vector of variances, okay? And then you basically write this as follows. Again, so if you have equal priors, this falls away. If you have, if you assume that every variance or every like if the variance is the same for each of the dimensions or the classes, you can remove this and you can remove that. And you can simplify this problem again and again if you wanted to. So here are the simplifications, I guess. So you can pool your covariance matrix, so this thing falls away because now this one is over all the classes, and sometimes you actually want to do that because if you don't have enough data points, you don't want to, like, so yeah, if you only have like 100 data points or 10 data points in one class and 50 in the other, it doesn't really make sense to compute separate covariance matrices for separate classes, so you sometimes just want to pool those guys. And then sometimes you just want to assume the independence across all the variables, so all the off-diagonal values are 0, so that means you only need to divide by a single number here, and then you can also assume that all the variances are the same, and that creates a Euclidean problem, basically, where you're removing the fact that you want to weigh dimensions with higher variance differently than those with lower variances. Okay, and we can also look at geometric assumptions or geometric visualizations of this. So if we allow each of the classes to have an underlying estimated distribution function that has various different covariance matrices, then we can learn these interesting curves. If we believe that they have the same covariance matrix, well, we learn a separation, and if you assume that the the covariance between all the so that we assume independence across all the variables, well then we don't get to turn these anymore, so we only can learn the different diagonals based off of like the stretching here. And if we do not assume any stretching anymore in all the variances, and the off diagonals are all zeros, well, we can only learn this kind of, so we can only learn by moving the distributions, okay? So it kind of like allows you to learn different separations, and the only way we can learn curves is basically by allowing the higher level covariances. And this is obviously in the two-dimensional space. All right. So let's take a 10-minute break before we get into the graphical models. And I think those are kind of interesting. Like, we're gonna mostly work on some examples to try to like get the basis of like these are graphical models in like a confined environment. We're gonna have an example that we work with, and we'll see that we only need a few values to model entire distributions over multiple variables. We're heavily going to use the Bayes rule and some other things. And then at the end we're going to extrapolate this to like any type of graph, but that's more or less like something that we might not really need in the future. Alright, so let's come back here at 11.